This is the moon and sky as seen through a telescope by an observer in Boston. And here, the moon and sky as a viewer in Santiago, Chile, would see it. Put these two views together and you have an overlapping double image. What can we find out from this image? Could it possibly be a key to finding the scale of our solar system?
Astronomers say that the sun and the innumerable stars we see at night are all at different distances from us. Yet here we are, bound to this earth, incapable of rising over it for more than a few miles. Isn't it one of the most incredible things in science that astronomers should have been able to find out how far away this sun is? Let us hear how that was done.
I want to describe how astronomers have made one of their most important measurements, the distance from the Earth to the Sun. When astronomers talk about this distance, they dignify it by using the imposing term, the solar parallax. What is parallax? Well, you can observe it very easily. Hold up one finger at arm's length and look at something on the other side of the room. First close one eye, then the other. You can see how your finger seems to shift from side to side against the background. That shift is the parallax of your finger. And in fact, parallax is the Greek word for shift or alteration. The parallax of your finger, then, is the angle made at your finger by the two lines of sight, one from your left eye and the other from your right eye. Now bring your finger nearer your face and repeat the eye play. Notice that the shift is greater now. You could use this shift, or parallax, to estimate how far the finger is from your face. The nearer it is, the larger the parallax will be. With this in mind, let's look at the sky. If you want to detect the parallax of an object in the heavens, it is easier to look at one that is nearby. Let's choose the nearest, the moon. Since it is near, its parallax will be relatively large, and it will be easy to see and measure. Here is a model of the moon. This time you can't estimate distance by closing your eyes alternately. Our eyes are only a couple of inches apart, much too close together to give any shift effect for the moon. Instead, let's place two observers as far apart as possible, on opposite sides of the Earth, nearly 8,000 miles apart. Here is what each observer will see. You see, our observers get slightly different views from their different spots. Now look at the background of stars in the far distance. You can see the moon shift positions against that background. Now, if you can measure the size of this shift, you will be able to find the moon's distance. The first problem here is how to fix positions in the sky so you can determine the angles of this shift. Well, astronomers do it in just the same way that we fix positions on the Earth. Hawaii, for instance, a spot on the Earth, we say that it is at latitude 20 degrees north and longitude 155 degrees west. Latitude is measured from the equator and longitude from an arbitrary fixed circle that runs through the poles. Here's a cross-section of the Earth. The longitudes are marked around it, covering 360 degrees to the circle. You can see that they are expressed as angles. Latitudes are measured the same way. Astronomers look at the starry sky as if it were a vast globe encircling the Earth. They draw an equator in the sky and also an arbitrary circle that goes through imaginary celestial poles. They measure positions of this star map from these two lines, just as we do on Earth, from longitude and latitude. Therefore, the positions of stars and distances between stars are measured as angles in the sky. Now you can see how the moon's parallax is measured. Here we have the distance between two observers. That is the diameter of the Earth. Here is the moon. And here, the distance between the two positions of the moon as you saw it against the stars measured as an angle. So now you can draw a triangle and find this distance from the Earth's center to the moon's center. We know the length of the base of the triangle, the diameter of the Earth, 7,900 miles. Since we know the base angles of the triangle, we can draw the whole triangle and, by simple trigonometry, can calculate the height of the triangle, the distance to the moon, which turns out to be about 240,000 miles. It is clear that once you can determine the parallax angle of an object in the sky, you have really solved the problem of how far away it is. The moon is a fairly easy subject. When we try to measure the distance to the sun, the problem is a great deal more difficult. I'll show you why. Here you see the disk of the sun. And now you can see the shift of the disk as seen from opposite sides of the Earth. Notice how small it is. Even if you could see the star background, which you can't, the solar parallax would be almost impossible to measure. So you have to use a roundabout method. Suppose I show you a map of a section of the Maine coast with a scale missing. Imagine you are here and want to know how far it is to this island. What could you do? The island is inaccessible. You cannot go there and measure the distance. But you can go here and measure this distance. All right. Suppose that distance is 10 miles. Then you can measure how many inches it covers on the map, and you find that it is 2 inches. Then you only need to measure the inches on the map to the island, say 8 inches, multiply, and you find that the island is 40 miles away. Can you play a similar trick in finding the distance to the sun? Could you make a map in the correct proportions? Even if you didn't know the scale of this map, possibly you could find a distance that can be determined, and so determine the scale. Well, this is exactly what astronomers do. Here is a model of only part of the solar system. If we had included the whole system, it would have been much too big to handle. The sun is here in the middle, and the planets are going around the sun in orbits. Here is the Earth in its orbit, and here is Mars in its orbit outside the Earth. Now, I'm going to move the two planets so that they're both in line with the sun. Now, let's move Mars and the Earth around until they are in line with the sun again. Astronomers call the interval between the times when the sun, Earth, and planet meet again in a straight line the synodic period of the planet. Synodic comes from a Greek word which means a meeting place. Now, since the Earth moves faster than Mars, it will go around its orbit almost twice before it meets Mars again. In other words, it will take almost 2 years before the Earth will be in a straight line with Mars and the sun again. It is easy to measure this synodic period of Mars, 780 days. But the synodic period doesn't tell us how long the planet takes to go around the sun once. It only tells us how long it takes for the planet, Earth, and sun to line up again. To map the orbit of Mars, you must observe Mars from two different positions when it is at the same point in its orbit. And when it is at that same point, the sun, Mars, and some distant star will be in line. But as you can see, the Earth and Mars, the Earth has gone round twice now, won't be in the same relative positions on the two separate occasions. Here they are with Mars at this point, lined up with stars over there. Now if you carry Mars around once and back to the same place, the Earth will have gone around nearly twice and will have arrived here. So we shall see Mars against a different background of stars. The problem is to find when will Mars be at a given point in its orbit. The answer is that it reaches a given point regularly every time it makes one trip around the sun. This interval is called the sidereal period of the planet. How do you find this period? Well, let's look at it this way. The Earth's sidereal period is 365 days, so that it goes 1/365th of the way around its orbit in one day. Now let's call the sidereal period of Mars X days, since this is the unknown in our equation. Mars will go 1/x of the orbit in one day. Now you know that the Earth goes around faster than Mars, so it catches up with Mars by 1/365 minus 1/x of the circuit in a day. But we know the whole synodic period. In other words, the time taken by the Earth to catch up with Mars again. It is 780 days. So in one day, the Earth catches up to Mars by 1/780th of the circuit. Now here is your equation. 1/365 minus 1/x is equal to 1/780. And the answer is x equals 687. So now you know the sidereal period of Mars, the time it takes to go once around the sun, 687 days. Now you only need to pick two dates, 687 days apart, and you can observe Mars and know it will be at the same point in its orbit both times. Now look at the model again. On the first date we choose, Mars and the Earth are here. I'll make a little mark to show where the Earth was. 687 days later, Mars has gone around once, and the Earth has gone around not quite twice and is here. Now you have two different angles you can measure by viewing Mars against the stars from the Earth's two positions. And you can draw this triangle with Mars at the apex. We also know the angle between the two positions of the Earth. We know the time that elapsed between this date and this one. We subtract a year because the Earth has gone round more than once, and divide a year by the interval that is left and get this angle. So we know this angle, we know these two angles, and we can draw this whole quadrilateral. We can now place Mars exactly. This is our first step. We have determined one point in the solar system, but we haven't determined the scale yet. We only know the shape of this quadrilateral and not its size. We could go on and plot the whole orbit of Mars in this way by measuring directions to Mars at pairs of dates that were separated by 687 days. and you get a number of other quadrilaterals like this one. In fact, this is how Kepler first did it. You can also map the orbits of the other planets and produce a map of the whole solar system. But what is the scale of this map? You still don't know the distances. You still want to find the distance from the Earth to the Sun. Remember the problem of determining the distance of the island from a map of unknown scale. There you found a distance you could measure, and you found the scale of the map by measuring that distance on the map. You can do exactly the same thing with the map of the solar system. What you need to find is something in the solar system that has a rather large parallax. This means, as you remember, something nearby. Mars and Venus are the nearest planets. But even the parallax of Mars is quite small, equal to its apparent diameter when Mars is nearest to us. Mars also is difficult to measure because it is not equally illuminated by the sun. It shows slight phases, in other words. In spite of these disadvantages, Mars was the first planet used to measure the scale of the solar system. Mars was observed from two widely separated places on the Earth. The angle of shift against the stars was measured, and the distance of Mars was calculated in the same way as we determined the Moon's distance. With this newfound distance, the distance between the Earth and Mars, you can fix the scale of the big map. In fact, you can determine the whole scale of the solar system, and we find that the distance from the Earth to the Sun is about 93 million miles. But astronomers kept looking for a closer object than Mars by which they could measure this important distance. In 1897, they found one, a small planet which they named Eros. The orbit of Eros is an ellipse. At intervals of 683 days, it comes inside the orbit of Mars, as you see in the model. When the Earth is at the right part of its orbit, Eros passes quite close to us, and its parallax is nearly 3 times that of Mars. This happened in 1931. The parallax was so large that it could be measured accurately by using the diameter of the Earth, as we did for the Moon. And since Eros is so small, its position was not difficult to fix against the background of stars. The thousands of measurements taken of Eros give us a new determination of the distance within the planetary system. The distance of the Earth to from the Earth to the Sun, 93 million miles, is now known within about 5,000 miles. The solar parallax is a very important quantity to the astronomer. It is the basic unit to which all other distances in the universe are referred. Naturally, astronomers would have more than one method of measuring such a difficult and such an important quantity. Actually, there are 2 or 3 other ways, but here is just one of them. Imagine the Earth as if it were a train running around on a circular track. Now you want to find the distance across this track. If this were the Earth, the diameter of the track would be twice the distance from the Earth to the Sun. Well, you can find out the distance around the track, the circumference, immediately, if you know how fast the train is going and how long it takes to get around the track. Suppose the train is going at 60 miles an hour, and it takes 10 hours to go around. Then you know that the track is 600 miles around. And from this point, you can use the well-known formula: the ratio of the circumference to the diameter of a circle is equal to the constant pi, or 3.14159. So if you could find the diameter by dividing this circumference by pi, you would know the size of the track. Now, you know how long it takes the Earth to go around its track. It takes a year. If you could measure the speed of the Earth, then you could calculate the circumference and the diameter of its orbit at once. But can you measure its speed? Astronomers do it by using a property of light which is called the Doppler effect. Have you ever noticed the sound of a train whistle as it passes you? The pitch of the sound drops abruptly. You hear this because the waves of sound crowd up towards you as the train approaches and thin out as it recedes. The more crowded the waves are, the higher the pitch of the sound will be. If you had a good enough ear or some way to measure the pitch, you could even measure the speed of the train by measuring the change in pitch. Now, we happen to have here a record of the sound of a jet plane as it comes from far away on our left, passes at some distance in front of us, and goes away to our right. This sound effect is not as simple as that of the train because the speed with which the jet plane first approaches us and finally recedes is changing continuously. The sound you will hear is very high-pitched at first, goes down gradually, and settles down at a lower pitch. Listen. Let's hear it again. Now, how does this relate to the stars? Of course, we can't listen to the stars, but they do send out light. This light comes in waves, which are affected in the same way if the light source moves. When the light source approaches you, the light grows somewhat bluer. When it goes away, the light becomes redder. Astronomers can measure accurately this bluing and reddening of light and determine the speed of the source, or star. The greater the change in color, the greater the speed. Suppose you are out there. You receive light from the Earth. You measure the change in color and find the speed. At this point, the Earth seems to be approaching you at full speed. At this point, it would be receding from you at full speed. So it is possible to measure the speed of the Earth in its orbit, and then you can find the circumference of the circle. And you can multiply the number of miles a second by the number of seconds in a year, and that gives you the circumference of the Earth's orbit. Then, of course, you use the pi formula to get the diameter of the Earth's orbit. And there you have another way of determining the solar parallax. But wait a moment. You cannot conduct an observation from a star. However, you can observe that star from the Earth. And as the Earth moves around in its orbit, you will see the star appear to approach you when you are here and to move away from you when you are here. Actually, of course, the star is stationary. Therefore, the speed you measure by watching the light shifts of a star is actually the speed of the Earth in its orbit. So, you have again solved the puzzle of the distance to the sun by observing the light shifts of a star far away. You've seen several ways in which astronomers have measured the scale of the solar system. We measure the distance to the moon and the distance to Eros from opposite sides of the Earth. Here, in other words, you used the Earth's diameter, 7,900 miles, as a baseline. In this way, you determined the scale of the solar system and measured the distance to the sun. Now you want to go out beyond the solar system to the stars. With only our humble yardstick of 7,900 miles, we could not possibly observe the parallax of anything outside the solar system. Indeed, we cannot even measure directly the distances of most things inside the solar system. But the jump from 7,900 to 93 million miles extends our reach enormously, as far as the nearest stars. From opposite sides of the Earth's orbit, you can see a small parallactic shift for several thousand stars. It is very small. Even for the nearest star, it is less than a minute of arc. And remember, there are 360 degrees to a circle and 60 minutes to a degree. So there are 21,600 minutes of arc to a circle. And you have to be very accurate indeed to measure an angle as small as 1/21,600th of a circle. But still it has been done for several thousand stars, and we can tell their distances and their true or absolute brightness. You can measure the distance to one star and then pick out another similar star. Assuming its brightness is the same, you can deduce its distance, even though the star is so far away that its parallax couldn't possibly be measured. In this way, astronomers have stepped from one measuring stick to another and are now measuring distances out to the farthest observable objects in the universe.
Well, here we are then. The impossible has happened. And astronomers have found out, without leaving the Earth, that the Sun is 93 million miles away. Why did this seem so impossible in the first place? I would say that that was because when you and I look at the stars, we do so for 1 minute at a time. That means we don't really know them. But if you keep observing them night after night, as astronomers have done from the earliest Assyrian times to ours, then you become familiar with them and you begin telling them apart. Later, much later, you find regularities even in the irregular wandering of Mars. And this, Mrs. Gaposchkin told us, is how the problem began to be unraveled. Still, without two technical devices, the telescope and the photographic plate, astronomers could never have obtained such precision as measuring 93 million miles within an error of 5,000. Such a result was a triumph of astronomers of our own generation. In astronomy, at any rate, we find no ground for being ashamed of our age.
This is National Educational Television.